This is the concept of the second law. We're writing it now in terms of energy value, and it's used to us. We now are going to switch gears a little bit and talk about energy and how well I can use that energy for my benefit or society's benefit, your benefit, whoever wants to use it. So we're going to look at the Carnot Cycle. Carnot Cycle or Carnot engine. So in this case, in the late 1800s, late 1700s, early 1800s, there's someone named Sadi Carnot. And he was in the Napoleonic era, so he happens to be French. And he was thinking about the steam engine. So at that time, the steam engine was just coming into being. And the steam engine is where steam was used to make a reciprocating engine move, and he wanted to look at the theoretical foundations associated with that. So he wanted to come up with something that he could use as a model. And so what he came up with was the Carnot Cycle. And if I look at that cycle, and I take a piston cylinder, I'm going to look at a PV diagram. I'm going to start here at state 1. So if I start at state 1, and I'll use an ideal gas. So I'll use an ideal gas so we can write that. We know the equations for it. We just looked at it. And so to model the heat addition into looking at a steam generator, which makes the steam, and the reciprocating engine, he came up with the following. So he thought that there would be constant temperature heat addition. So this would be Qn at TH. So this would be the engine, and now the piston would be moving down here. So I'd be moving down here. Now I'm at a high, this is a very high pressure and temperature. Now this is a lower pressure, but I still have pressure, and I can have an adiabatic expansion, reversible adiabatic expansion down here. So now I'm down here, and this is a reversible adiabatic expansion. Oh, PV to the K. So I have reversible adiabatic expansion down here to the end of the stroke. And now, because this is going to be a 4-process cycle, as you remember from chapter 6 with the 3-process cycle, we have to get back again. So now we're going to have a parallel process to the heat in. We're going to have heat rejected. So now we're at a low temperature and a low pressure. We're going to now have constant temperature heat rejection from 3 to 4, so here we're going to have Q out at TC, T cold, at a low temperature. And now we get back, we're going to have reversible adiabatic compression, PV to the K is equal to a constant from 4 to 1. So we now have a cycle where we put energy in, and this is W net. So we have something that enables us to look at this. And so now what we want to be able to do is to take this cycle and figure out an expression for it, how well the heat in got converted into net work, and that gives us the efficiency of the cycle. So the thermal efficiency is equal to W net over Qn, desired effect cost of effect. So all efficiencies are related to output over input, or what the desired effect is over the cost of the effect. The desired effect is produced work. The cost of the effect is the energy that we had to put in. And so now we needed to develop expressions for this. For a cycle, you'll remember that W net is equal to some Q. So if I'm able to find Q in and Q out, I can add them together and get W net. And so Q in, so Q in is where the temperature is constant, TC, TH, where the temperature is constant at a high temperature. And so I want this to be going in at a high temperature. And so this is equal to, and a constant temperature, we remember from chapter 6, we had an expression for heat in for a constant temperature process. And so Q in was equal to mRT1 times the log of V2 over V1. And if I look at this, T1 is equal to TH. So that's equal to TH, so I see I have a TH term here. So this is my Q in, my Q out occurs between 3 and 4. So now I have Q out. Again, it's an isothermal constant temperature process. So yeah, I start at the initial mRT3 times the log of V4 over V3. So we have equals mRT3 times the log of V4 over V3. And I notice that T3 is equal to T sub C. And so I see that I'm going to have a TH and a TC in there. If I look at these relationships, they're relationships between the volumes. And so if I do some algebraic manipulation, which I'm not going to do here, I come up with that the thermal efficiency, W net over Qn, is equal to 1 minus Tc over Th. So it's a very simple expression. So I combine this. You can look in the book and it goes through how to do all the algebra. I'm not doing the algebra here. Many people do not pay attention to the algebraic niceties. And so we have an expression. This is a worthwhile equation to note. And if I look at this just conceptually, this represents Qn. Where did the heat go to? Some of the heat was converted into work, W net. The rest was rejected as heat out. And so this is what happens. The energy that went into the Carnot engine and the first process, some of it got converted into net work, the rest left the system. And we'll do an example in just a short while. They're easy functions to work with.